First of all, thanks a lot for the invitation. I'm very happy to be here and virtually and present this talk to us. And yeah, I believe I don't need to further raise your interest for digital assets like Bitcoin or other cryptocurrencies. Uh, that this seminar exists and that we are talking about interesting cases such as tax evasion or in general the relation to central bank issued money and all the talks about it shows that there is a great relevance for this, not only for the general public but also especially for us as researchers. Um, while personally I don't really own any significant amounts of cryptocurrencies, as a researcher, the insane volatility, the speculation around it, and also the frequent bubbles are raising the question: how do we price these beasts of assets? Yeah, I mean, I'm pretty sure not everyone in this room is into option pricing, but what it can help us do is basically getting rich if we're doing it right, but we can also avoid at the same time getting poor if we do it right. And yeah, I mean, at least that's what my investment banker friends are telling me. Those of you who are familiar with the domain would probably agree with me, though, that what we usually do is we take historic data and then fit some simpler or more complicated model that describes the underlying process. And I'll just assume not everyone is familiar with what's an option. So before I walk you through the model, maybe let's first quickly talk about what's an option. Yeah, in short, an option is the right or the duty to buy or sell an asset at a future point in time to a certain price. And we can easily construct an example where, for example, we have an option to buy 1 Bitcoin. We love Bitcoin. We want to buy it. So we have an option to buy 1 Bitcoin for $30,000 on May 31. So 30 days from now. So the strike price of that option would then be 30K because that's the price at which we want to settle. And the moneyness in this option pricing world tells us whether or not the option is a good deal at the moment. It's a comparison between this strike price for the option and the actual asset price that we can look up, for example, on CoinMarketCap anytime. So just really shortly, what you need to know about it is that if it's greater than 1, we're in the money. If it's smaller than 1, we're out of the money. And if it's exactly 1, we're at the money. And the further away this ratio is from 1, then the further away is also the actual asset price from the price at which the option is settled. And options far away from the number of 1, so from the money itself, are less likely to be traded. And the time to maturity then indicates how far away are we from the expiry of the option. In our case, the time to maturity would then be 30 days, as said. So yeah, that's just a very basic. Yeah, why were we talking about it? Because this talk is about pricing options of Bitcoin. And in order to price such options, as previously mentioned, what we do is usually we take historic data and then fit some kind of model that just aims at describing the underlying process. And this methodology has been extended to cryptocurrencies by an ever-growing branch of research, but none of that research so far had considered that, according to newer findings, buying pressure in cryptocurrency markets comes mostly from informed traders. And while we can't access their knowledge directly, we can kind of observe it through tracking a metric called implied volatility. And what you see here on the slide is just such an example. Like, we will not go into the details, but it's just an example for like how you would look at such an option pricing model, right? A lot of mathematical equations, and we'll get to that in a second. Let me just quickly explain to you also what's implied volatility. So for those not familiar with it, it's a theoretical value for volatility that when you plug it into an option pricing model like the famous Black-Scholes, it gives us the current market price. So we can observe everything except for this implied volatility. And when we have that, we can solve for the market price. And now remember the moneyness. So say if 1 Bitcoin would be currently at $15,000 to buy on an exchange, I just checked on CoinMarketCap, let's say it's that price, then our plan is to get an option to buy 1 Bitcoin, but cheaper than the market price at some point in the future. If now we we would see an option with the right to buy 1 Bitcoin at $30,000, then we would need to believe that this asset is extremely volatile in order for us to buy this option and think this could make us money. So I hope this example was clear. Just in a nutshell, the implied volatility is useful for us in a sense because it shows us how likely we are to reach certain prices of the asset according to traders. Hope that makes sense. Yeah, so let's move back to the core of the approach. I think what you need to take away basically from the slide is just that there are option pricing models. They help us describe a process, and it usually this process usually does like some zigzagging movements in a certain range, kind of like when you see a drunk person walking home on the pavement, sometimes moving left, sometimes moving right, but in the end reaching their destination. And yeah, that is the Brownian motion. That concept is called a Brownian motion. And then we have the volatility additionally, that is kind of the range on which the drunk person is zigzagging. And we could then say that kind of describes how broad or narrow the street is. And yeah, however, sometimes these zigzagging movements are interrupted by strong shocks, either upwards or downwards. And these shocks are jumps in a model. And I'm going to get back to this topic also in a little bit. Essentially, what we just want to do here is estimate 3 functions. They are called mu, gamma, and eta. They tell us something about the mean of the process, about the changes in the price process, and about the volatility dynamics of the process. Yeah, maybe just because I know that this is all maybe a lot also to take in. Where we are currently is we have a certain desire from a financial mathematics perspective to price cryptocurrency options, because that helps us say something about whether the instruments we see on the market, if they are fairly priced or not. And we can use some metrics like the implied volatility to calculate that. But there were some backdraws in the past, mainly the reliance on historical patterns that are not really useful in the case of digital assets because they are so crazy volatile and there's so much external influence coming. And that's why we are looking for new ways. And using these kinds of implied stochastic volatility models is then a new way on how to do it. But there are, yeah, and in the end, what is of relevance for us is estimating certain functions in the end. Yeah, for now, let's pretend that it's not such a complicated case where like jumps are not an issue. And then I'll quickly just walk you through the approach of pricing such a cryptocurrency option. Having the previous model in mind, we can estimate IV surfaces based on information on time to maturity, that is tau, and the moneyness, for convenience here as a logarithm. The equation gives us the IV surface where the IV value for each time to maturity and each moneyness individually is displayed. So this in the end would look like a surface actually. So you can imagine it just on a 3-dimensional plot, and you would see for each time to maturity and each moneyness, you would see then a different value, and it would be some kind of surface. And we can use this information then to deconstruct if the options we see at the market are fairly priced. And if they are not fairly priced, we can make money out of it. So, but now why we were saying before that jumps are problematic, well, the thing is we can include them into this theoretical model, and that's also a pretty standard approach in asset pricing and financial mathematics. But in the context of ISV models, such jumps are limited to the return dynamic. And accounting for other factors would require substantially altering this procedure and then extending the theory behind them also. So this makes them incredibly inconvenient to deal with, and it ruins our model basically. In order to then account for these jumps, the current procedure would require extremely high frequency data that is at the moment impossible to obtain due to liquidity constraints in digital asset option markets. Additionally, jumps in digital assets are still not very well defined due to the unique market microstructure of digital asset markets. And to overcome these empirical and theoretical challenges, we instead propose fitting multiple models under various volatility regimes where the subset of each time series then have a stable characteristic. Yeah, and this can be done then by identifying different regimes in the data. Again, we will not get deeply into the mathematics of it because the general idea is more important. There are many ways to deal with having different regimes in the data, and yeah, empirical research on crypto suggests though that current methods, for example, for finding jumps, saying, okay, there's a COVID crisis, and after that and before that, there's a different market. That's pretty complicated to do because the data in digital assets is so complicated. We instead say that since at each point in time, we have many different options. So like some expire in a week, some expire in a month, some in a year, and at many different prices. We have a lot of highly correlated options that there are then different volatility, so different states of this volatility measure. So for simplicity, maybe let's just keep it at like there's high volatility that is during some crisis period like COVID, and there's low volatility. So during some very quiet periods, like you could imagine more now. And yeah, what we here is also a pretty typical clustering approach where for each point in time, we we have clusters, and then we determine to which cluster each observation belongs based on a covariance structure. And we can do this iteratively through the whole time series, and only need one hyperparameter lambda that stabilizes the data basically and punishes if you want to move from like a high volatility state to a low volatility state. And we infer the state based on a sparse precision matrix at each point in time and enforce stability through this penalty. And then we just calculate the smallest log likelihood distance with respect to the student T distribution and a switching penalty. Yeah, and basically then we can determine for each observation to which cluster it belongs. Maybe to sum up everything so far, our approach is to first cluster the data into the time series into different clusters, and then we fit like such an implied stochastic volatility model for each cluster individually. And this way, then we don't have any more jumps or like shocks in the data, and we are able to fit our option pricing model based on implied volatility anyway. Let me just have this for you for a second so that you can have a look at it. So yeah, empirically we tested the procedure on a data set from April 21 to March 22, and that's roughly 1 year of data, which you see here on the left-hand side. So what you see here is an example of such data. We took always rolling windows of 5 days at a frequency of 20 minutes, and yeah, so what you see here in these colors is probably a bit confusing, so let me walk you through it. On the left-hand side, you see the implied volatility measure, the one that I described to you before. And remember, like we want to be roughly around 1 for an option to be traded. And each of these colored line is represents the IV evolution of an option with a specific strike price and a specific time to maturity. And on the y-axis is the implied volatility, as said. This is just 1 5 days rolling window, and we filtered out only to have observations where the time to maturity is less or equal to 1 week, and the moneyness is between 0.8 and 1.2. So yeah, the idea is we are interested in options that are close to expiry, because of course we want to make money now and not later, right? And having this data in mind, so having like many of these 5 days windows, we fix K and lambda for each of these windows, cluster the data with the presented algorithm, and then fit like an ISV model for each state inside this data individually. And let me show you also how that looks. We demonstrate the result of this clustering based on 2 different time series at each point in time for these 5 days rolling windows. This is also just an example out of the data. On the left-hand side, we see the evolution of the Bitcoin US dollar exchange rate. And on the right-hand side, we see, again, the same options as before with different expiries and strike prices. And the colors now represent the different states. What we see here is that observations have been assigned to 2 different regimes. And each of these regimes appears to be fairly different when looking at the magnitude of price movement and the spread of IV in options. Now, what does this mean for our model, the one we talked about before? While in the red cluster, the price process seems to be very volatile. Interestingly enough, the IV for different prices, like so, the part on the right-hand side, seems much closer together. And as the time to maturity reduces, so we are getting closer to the settlement of these options, while the price process seems to stabilize, the IV values are spreading out further. I think that's pretty visible, right? If you look at the green parts in the price plot on the left-hand side and the green parts in the IV plots on the right-hand side. Yeah, so looking maybe at some goodness of fit criteria, let's consider the case of the root mean square error, or short RMSE. What the table shows us here is the distribution of this RMSE inside the sample of the functions that we wanted to estimate. So just to remember, so mu tells us something about the mean of this process. Basically, so the mean of this price process here. Then what we have also is oh, sorry, just a second. Yeah, so what we also have is the other functions, eta and gamma, that tell us something about the price process itself, like the magnitude, the volatility of it, and also the magnitude of the volatility process. I hope that's clear. So what the table shows that first on the very left, we see the function estimate. At first, always in the unclustered case, and below that for cluster 1 and cluster 2. And we evaluate the goodness of fit based on the mean, the 5th percentile, 95th percentile, and the difference or the spread between the higher and the lower percentile. And in case you are wondering why we are looking at the whole distribution, this is because we were fitting. So here we are fitting for each point in time, we are fitting one model, and that gives us a whole distribution of values, right? And yeah, what the results basically show us here is that for each of the functions, the distribution of values is more stable when we use clustering as opposed to not using it. And this applies both to the consistently lower means in the clustered case and the smaller spread between the higher and the lower percentile. Maybe looking also at the fits of the regression models, we see a very similar picture where on the left-hand side, we see the function fit for the unclustered model. And on the right-hand side, we see the function fit for cluster 1 and cluster 2 respectively. And even if we're just using eyeball econometrics here, it's pretty obvious that clustering improves the data fit significantly. And that kind of further proves that our method is effective at solving these problems of non-stationarity and frequent shocks in the market. And yeah, I mean, our intention in this talk was not to go deeply into the technicals, but more like to demonstrate that this is a feasible approach that also opens up possibilities to use the aggregated knowledge of informed traders in this complicated case of digital asset data. I hope we were now able to convince you. Actually, we have some limitations. So first of all, we only use ensemble validation, and we also didn't compare this model really with other models. Both of these are items planned for further research. But what we really want to do is we want to encourage researchers to shift the attention to further exploring high frequency setups and also the econometrics of these super exciting digital asset markets. And in that sense, thank you very much for your attention. And yeah, please feel free to ask any questions you have.
Thank you. Let's jump straight in because we're a bit short in time. Do we have any questions? No? No, good. Maybe I just ask one quick question. So maybe I missed it where you I get the general idea that that you're gonna you incorporate regime market regime switching into price into option price pricing. That's the basic idea, right? But how would that be applicable to real world pricing in the sense that if you have a new option, how would you know kind of what the current market regime is without having all the relevant data, or would you just use the past data to get the kind of what the current market regime is, or how exactly that's conducted?
Yeah, I think that's a super interesting question, and that's also something we were wondering, because what we basically just showed is that if we know the regime already, then it's fairly easy to say, okay, that's how we price the model. But actually, the interesting question is, what is the next regime, right? And yeah, we were experimenting a bit with this already, in the sense that you can also, like, you can try it based on a likelihood or something, based on some characteristics, to say, okay, it's more likely to belong to this state or that state. Yeah, it is definitely some item for further research, but I would say, yeah, you can do it maybe like likelihood based or one step ahead, basically, based on the previous observations. So in a dynamic way, but yeah, I think it would be interesting also not only to do this empirically, but to establish some kind of theory based on which you could like really forecast these next states accurately.
Okay, thanks. That answers my question. So it's an avenue for future research.
Thank you exactly. Yeah, thank you so much. And apologies if I overextended my time slot.